Hello and welcome everybody. My name is John Metelsky. This presentation is called M-Test, an alternative non-parametric test for two independent samples. So my plan for the presentation is to discuss the motivating statistical question, review mann, whitney, U, and Kolmogorov-Smirnov tests, show you the idea behind my M-Test, compare their performances in a number of different situations, and then offer some concluding remarks. So the motivating statistical question is, given two data vectors, S1 and S2, how unlikely is it that they share a DGP? Is there evidence against them having the same data generating processes S1 and S2? This might seem like an overly simple question that anyone with a first course in statistics would know to use the t-test or whatever. It's a very simple question, but in a sense it underlies a lot of more advanced statistics. Can we tell if two things are different or not? So the student's t-test, or the parametric approach, is to say, okay, let's assume everything comes from a normal data generating process. Ask if there's a statistically significant mean difference for the two vectors. And if so, it's unlikely that they share a data generating process. The non-parametric tests take a bit of a different approach. They consider the ordinal configuration of the data, how the data rank on a number line, and then ask questions about how integrated the data are. Like, if there's no overlap in the data, they probably don't come from the same process, and if there's a lot of overlap, there's a good chance that they do. So the idea is to map from the outcome space to a test statistic, and then on to a probability so that we can make inferences. So configurations of the data, mappings, what am I talking about? So the idea is, let's consider just a very simple case where you have 4 IID data. In this case, they don't look so IID, they look more like 1, 2, 3, and 4, but that's because that's what they are. But in any case, this is representative of the ranks of any random variates. Okay, so there are 6 different ways that this could happen completely randomly. So what I'm suggesting is, if you had a random number generator and you got 4 random numbers and you're not looking at them, you don't know the actual instantiations, you just know you have 4 of them, and you decide to put the first 2 into one group and the second 2 into another group, and then you get to see what they are, and you lay them out on a number line. These are like the possible configurations for like how they grouped. And I want to point out that there's no inherent order to these configurations, and that they are essentially high-dimensional entities. In other words, in order to describe, say, the first configuration, you would actually need like a 4-element vector that tells you specifically blue, blue, red, red, or 1, 1, 0, 0, or something like this. So in the context of like typical statistical testing, such as the t-test, what we strive to do is to get a p-value, a probability of seeing data as or more extreme than what we saw. So the question is, in this context, like, what does that actually mean? Is configuration 1 as or more extreme than configuration 6? Or like, how would you attach probabilities to these? So how do these rank, and what are their probabilities? So further, I ask, is the modern toolkit, mann, whitney, U, and KS, sort of adequate to address this problem? So just to review those tests, mann, whitney, U is a location test asking whether one process is stochastically greater than the other. The idea is that if they are stochastically equal, they would have the same median, and the probability of seeing outrankings of a data in one vector relative to a data in another vector would be 0.5, and then you could just get the sum of the relative ranks for one of the vectors, and that's like the idea of how you're mapping from like the configuration of the data to a single number. So you sum the ranks. So I would normally demonstrate this with my hands, but you can't see my hands. If you had 5 5 and 5 data in each of S1 and S2, and you let your hands represent those. If you hold your hands completely separately and you do sum of the ranks using one hand as reference compared to the other, you'll get 0, 0, 0, 0, 0, or 5, 5, 5, 5, 5. So you'll get 0 or 25. So we see disintegrated data gives us sort of extreme test statistics and very integrated data. Like if your fingers were completely overlapping and you count the outrankings, it's much closer to 10 to, depending on how you hold your hands, it's going to be something central to that range. So Kolmogorov-Smirnov, by contrast, uses it's testing the sameness of the data generating processes, which is a bit more encompassing than the location test because it's sensitive to higher moments. So the reasoning is that if they are the same DGP, then the empirical CDFs that they're estimating should be the same, and the probability of seeing large differences should be small. So it's all about the distance between the empirical CDFs. And the idea is you're mapping the outcome space, the configuration of balls, basically, into distances between the empirical CDFs. Discrepant data are going to give you large maximal differences, and vice versa. Okay, so this is my idea for how to map from the outcome space to a number and then to a probability. So the M-test is specifically asking whether the pooled data form an IID sample. So you started with data vectors S1 and S2, and I'm saying put them all together into a big set P, and the question is does this set agree with the assumption of an IID sample? So if, in fact, P is an IID sample, then theorems about the probable location of the median, that is, that it follows a binomial distribution, will hold for all three sets, P, S1, and S2. So the probability of seeing large maximum distances between these distributions should also be small. So I've mentioned you're getting like three different sort of ideas of where the median is. How do you get the distance between those distributions sort of collectively? And what I suggest is you want to consider the probable location of the median under the pooled data. And then you want to look at, when you partition the data, those two assuming things happened randomly, those two are like not dependent, but have like kind of an odd sort of dependence in that they share the same parent, the same pooled data. So my idea is to look for the distance between the probable location of the median relative to the pooled data and the probable location of the median for like the normalized product of the probable location of the median under S1 and S2. Hopefully this will make sense at some point. Okay, so here's the visual idea. The top line here is the pooled data. It's been randomly partitioned into these two sets, S1 and S2, and the idea is if we multiply the second and third line and normalize, we get the distribution on the bottom here. And the point is, it's very similar to what we started with, but not identical. So there's been some, you might say, loss of fidelity by doing this process, but it's pretty close. And so the M-test statistic would be the maximum distance between the first and fourth distributions. Okay, this figure got a bit cut off, which is sad, but basically to simulate what those maximum distances are, if you did this repetitively, I used Monte Carlo simulation. So my data is 15 and 15, and what I show here is that you do get kind of an interesting sampling distribution of those distances, and there's like a tail area down here that you can't see that represents like the top 5%. So like with this in hand, we can then take any two data vectors from any DGPs and ask the question of whether the pooled data form an IID sample by comparing it to a distribution such as this, but generated for the sample sizes in question. Okay, so now we move on to the actual simulations. For each simulation, I'm doing 10,000 replicates for each sample size or alpha level. For type 1 error, the sample size is set to 10, and for power, I'm using 0.05. I reset the seed in R for each simulation. Okay, so comparing normal DGPs, that means that S1 and S2 are both coming from a normal DGP, in this first case with equal parameters. So now I'm looking at the mean. So this is like the result of the first simulation. It's like this table and this graph. That's really it. So what's happening here is I'm looking at the mean absolute deviation of the empirical type 1 error rate. And I'm varying alpha along the x-axis. So basically each from 0.01 to 0.1 by 0.01. So basically I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 separate simulations of 10,000 replicates. And what we want to see here is flat lines that are close to 0. And I say that because if I'm measuring the deviation from the stated alpha level, the idea is the test should be doing exactly what the alpha level says. Like the definition of the rejection rate is, you know, the number of tests that I actually rejected, meaning the number of tests that produced a p-value less than 0.05. And so basically what it's saying is if the p-value you're getting from the test is actually the probability that it claims to be, then the mean absolute deviation of the type 1 error rate from alpha should be 0. So anyway, here we see that most of the tests are pretty well behaved. They stay relatively small, but the exception here is the KS test, which has the sawtooth appearance and a peak at 0.05. So if we look at alpha equals 0.05, the KS test has a mean absolute deviation of type 1 error rate that's at almost 0.4. So that's on the same order of magnitude as alpha itself. So I would conclude that one should probably be a bit cautious of what the KS test says at alpha 0.05, because it seems to be a bit miscalibrated. Okay, normal distributions, power to detect a location shift. So basically I've just kept the mean of one of the normals at 0, and the other one is I think is 1.7. And so this is how, as we increase sample size, we gain power with all of the tests. So again, just to emphasize how sort of big the simulations were, I did 10,000 replicates with 4 and 4 for the samples, 10,000, 5 and 5, etc. So, you know, each one of these slots got 10,000 replicates as you move in X. Okay, and what we see is that the t-test is really the clear winner here. It's fairly dominant. Not just fairly dominant. It's definitely the best in this situation, which is not surprising because this is what it's designed to do. One thing I do want to note, though, is that all of the tests achieved 80% power by here. Okay, so by the time you have a sample, oh wait, that's a lie because this power dipped. Sorry, it's right here. Okay, so as you get 11 people in your sample, all 4 tests that I looked at have 80% power to detect this location shift. So I'd say overall they're doing pretty well. Okay, power to detect unequal variance. So here I had the means of the normals were both 0, with the standard deviation of 1 for the first sample and of 9 for the second sample. Okay, so really that second sample had like a pretty huge variance compared to the first one. And what we see is that the KS test is the only test that seemed to get it, quote unquote. Meaning, even at sample sizes of 19, the other 3 tests were still under 20% power. See, I'm reading this right off the graph. I don't have this written down. Okay. Oddly, my test had like this spike at 5. But I mean, who cares? Because 23% power or whatever isn't going to get you very far. If you thought you only had 23% power, you would like go back to the drawing board and figure something else out. Because you're probably going to miss the effect you're looking for, so something should change. Anyhow, you know, the KS test is the only one that was able to achieve anything like respectable power to detect that these normals had different variances. Okay, and we see it's the winner for the sort of overall average power. Okay, moving on to some other more interesting stuff, exponential versus exponential distribution. So again, I start with equal parameters. So in this case, the rate parameter is 150. And when I look at the mean absolute deviation of type error, what do I see? Well, first, note that the curve for KS is exactly what it was on the first slide. And that's not because I messed up with my programming, it's because the KS test behaved identically under the two different generating processes. This idea that they should have the same, that there's like behavior to the way the empirical CDFs would look if you partition data that was actually from the same process. This is invariant to the actual choice of distribution. KS didn't even notice that this data wasn't normal, in other words. But we see there are other changes. Before, the t-test was the most perfectly behaved. Remember, the red line sat down here near 0. And now that situation has sort of flipped, and it is now second worst only to the KS test. Now, I do want to just go back and see what happened with the other two lines. Okay, so it looks like really like the sort of what happened with the other two lines seems fairly similar, though again, note not identical. Like purple started on top, and then there was some kind of like jostling, but then purple also still ended up on top. Okay, now this test looked at two exponential distributions with different rate parameters, one of them being 30 and one of them 150. So my main comment here is that all of these tests, even the one that I sort of made up, do what I would say is respectably well. And by that I mean, if we look at power 80 across the board, okay, Wilcoxon got it at sample size 10, T at sample size 11, KS had some sawtoothing, so they had it and then they lost it and then they got it again. And my test hit 80% power at a sample size between 14 and 15. So basically, you know, everyone's achieving 80% power by a sample size of 15, and so, you know, I'm pretty proud that I'm able to get in there with these guys and not make a fool of myself. Okay, exponential versus chi-squared. So now I'm mixing and matching not only the parameters of the distribution, but the actual distribution. So this is exponential with rate parameter 150, which we know has an expected value of 150, and a chi-square with degrees of freedom 150, which should have expected value of 150. So this is a tricky one for these tests because there is no location shift, like in a way, and these tests, I'm not exactly sure what I should know what the variances are, but I don't. But they're not the same, and they have like different shapes. If you look at these distributions, they're like clearly not the same. And what we see is that, again, the KS test, without a location shift, the KS test is the only one that you would say is sort of all over this and like really can detect with small sample sizes and fairly respectable power that there's something not right here. Now, I would direct our attention, this is my one moment where I was sort of the winner, is on these very small sample sizes, I'm getting more power. But the main observation is, look, we're only talking about 15 to 30% power anyway. So this would not ever really probably be of any real-world use. you'd be better off just waiting until you've accrued like a larger sample than like trying to use one of these tests for a sample of 5. Conclusions, I'm not going to do that part. What are my take-home messages here for this presentation? Larger sample size does not always imply more. Oh, I forgot to show my best thing here is that for the for the t-test, we see that as the sample size increases, it actually seems to be like slowly losing power, which is very interesting because this contradicts what a lot of people assume is a fact, that more sample size means more power. Larger samples mean more power, rather. So the take-home message is big sample size, larger sample size does not always imply more power. The agreement between type 1 error rate and the stated alpha level varies with alpha level and with the test. Okay, so this should be noted for people who think that just sort of using alpha equals 0.5 doesn't have any implications for how the tests perform, that it's like an that it's a threshold that doesn't have implications for the rest of your testing procedure, because it does. We see from these graphs, most of these, all of my type 1 error plots, there were 2 of them, they all show not monotonic increasing functions, where what they should be showing is just like straight lines across. So that should be heeded. And lastly, I conclude that the M-test seems not really to offer any clear benefit over mann, whitney, U, and KS tests. So our modern toolkit, as of what I can say right now, is just fine, and there's no real need to like start using a new test. Okay, thank you.